Tonight, we're going to explore something that challenges the very foundation of how you think about size. The universe isn't just big, it's so incomprehensibly vast that even our most sophisticated measuring tools reveal only a fraction of what exists. And here's the unsettling truth. The scale we can actually observe might represent less than 1% of reality itself. Before we begin this journey through cosmic distance, if you find these explorations into the nature of space and scale meaningful, a quiet like or subscribe helps this channel continue creating these meditative dives into physics. It's a small gesture that makes these late-night conversations possible. Now, let's step into the darkness and see how far it really goes. Consider the most distant thing you can imagine. Perhaps it's a galaxy you've seen in photographs, or a star whose light has traveled for billions of years to reach your eyes. Hold that distance in your mind for a moment. That vast, almost unthinkable expanse represents something profound about the limits of human intuition. We evolved to judge distances we could walk, territories we could explore, horizons we could reach. Our brains developed sophisticated mechanisms for estimating whether a predator was 50 meters away or 100. But the universe operates on scales that render these evolved capabilities completely useless. The observable universe stretches approximately 93 billion light years in diameter. This number feels abstract, perhaps even meaningless, until you begin to unpack what it actually represents. Light, traveling at 300,000 kilometers every single second, has been journeying toward us for 13.8 billion years since the universe began. Yet the boundary of what we can see extends far beyond 13.8 billion light years away. This isn't a contradiction. It's our first hint that space itself doesn't behave the way our everyday experience suggests it should. Space has been expanding throughout cosmic history. While light from distant regions has been traveling toward us, those regions themselves have been carried farther away by the expansion of space itself. Picture a balloon being inflated. Draw two dots on the surface and begin inflating. The dots move apart not because they're traveling across the balloon's surface, but because the surface itself is stretching. Similarly, the most distant observable galaxies have been carried to positions roughly 46 billion light years away, while their light has been traveling the 13.8 billion years to reach us. This creates something cosmologists call the particle horizon. Beyond this boundary lies space that exists but remains forever hidden from our view, not because our telescopes aren't powerful enough, but because the light from those regions hasn't had sufficient time to reach us since the universe began. We exist within what amounts to a cosmic light sphere, beyond which lies an unknowable realm that may extend infinitely in all directions. As you listen, notice how difficult it is to actually picture this. Your mind might try to imagine the universe as a giant sphere floating in the empty space, with us somewhere inside looking out toward the edges. But this visualization fails immediately. There is no outside. There is no space beyond space for the universe to float within. The universe isn't expanding into anything. It's simply creating more space as it expands. The mathematics suggests something even more unsettling about scale. If the universe is flat, which current observations indicate it likely is, then it may be infinite in extent. An infinite universe means that beyond our observable bubble, identical copies of every possible arrangement of matter would exist somewhere. Not just similar arrangements, identical ones. There would be infinite copies of our galaxy, infinite copies of Earth, infinite copies of you listening to these words right now. The implications stretch beyond what comfortable human thinking can accommodate. But let's step back from infinity for a moment and focus on what we can observe. Within our cosmic light sphere, astronomers have identified structures that reveal the universe's architecture on the largest scales. Galaxies don't scatter randomly through space. They organize themselves into an intricate pattern cosmologists call the cosmic web. Imagine soap bubbles clustering together, creating a foam-like structure with thin films separating empty regions. The universe resembles this pattern, with galaxies arranged along thin filaments, surrounding vast empty voids. The largest known structure in the observable universe is the Hercules Corona Borealis Great Wall, a collection of galaxy clusters spanning roughly 10 billion light-years across. To put this in perspective, light takes 10 billion years to travel from one end of this structure to the other. This means we see one end as it existed 10 billion years ago, while the other end appears as it was 20 billion years ago, long before our solar system even formed. We're not just looking across space when we observe such structures. We're looking across time. This temporal dimension of cosmic observation creates a unique perspective on universal scale. Every distant object we see appears as it existed in the past. The Andromeda Galaxy, our nearest major galactic neighbor, appears as it was 2.5 million years ago. Light from the cosmic microwave background, the afterglow of the Big Bang itself, has been traveling for 13.8 billion years. When we map the observable universe, we're creating a four-dimensional picture that captures both space and time simultaneously. The cosmic microwave background represents the oldest light we can detect, emitted when the universe was only 380,000 years old. At that time, space had cooled sufficiently for atoms to form, allowing light to travel freely for the first time. This radiation fills the entire observable universe, appearing remarkably uniform in temperature with tiny fluctuations of only a few parts in 100,000. These minute variations represent the seeds from which all cosmic structure eventually grew. You don't need to fully grasp this temporal layering to appreciate its significance. The observable universe functions as a natural time machine, preserving the history of cosmic evolution in the light that reaches us from different distances. We see nearby galaxies as they existed relatively recently, while progressively more distant galaxies appear progressively younger, showing us how the universe looked at earlier epochs. The expansion of space itself adds another layer of complexity to cosmic scale. Space isn't static. It's been growing since the Big Bang, and this expansion has been accelerating for the past 5 billion years. This acceleration is attributed to dark energy, which appears to be a property of space itself. As space expands, it creates more space, which contains more dark energy, which drives faster expansion. This feedback process ensures that distant galaxies recede from us at ever-increasing rates. Current models suggest that objects beyond a certain distance are already receding faster than light can travel through space toward us. This doesn't violate relativity, because the galaxies themselves aren't moving through space faster than light. Rather, space itself is expanding so rapidly that the distance between us grows faster than light can cross it. These regions have passed beyond our cosmic horizon forever. No signal they emit today will ever reach us, no matter how long we wait. This creates a paradoxical future for cosmic observation. While the universe grows larger, the observable universe will appear to shrink. Distant galaxies will fade from view as their light becomes too redshifted and stretched to detect. Eventually, only our local group of galaxies will remain visible, held together by gravity against cosmic expansion. Future astronomers will look out and see a much emptier, lonelier universe. They'll have no way to know that the cosmos was once filled with billions of other galaxies. We're fortunate to exist during an epoch when distant structures remain visible. In a sense, we live during a golden age of cosmic observation, when the universe's large-scale architecture can still be mapped and studied. This temporal perspective reminds us that our view of cosmic scale is not only limited by distance, but also by the particular moment in cosmic history we happen to occupy. The tools astronomers use to measure these vast distances reveal the ingenuity required to map cosmic scale. Standard candles, like Type Ia supernovae, provide crucial calibration points. These stellar explosions reach predictable peak brightnesses, allowing astronomers to determine distances by comparing how bright they appear versus how bright they should be. Cepheid variable stars pulsate with periods directly related to their intrinsic brightness, creating another type of cosmic measuring stick. For the most distant objects, astronomers rely on redshift measurements. As space expands, it stretches the wavelengths of light traveling through it. The amount of stretching indicates how much space has expanded since the light was emitted, which correlates with distance. Recent surveys have mapped millions of galaxies using this technique, creating three-dimensional maps of cosmic structure across billions of light years. These measurement challenges accumulate uncertainties that grow with distance. Our knowledge of the universe's largest scales carries significant error bars. Recent observations have begun to reveal discrepancies between different measurement methods, suggesting that our understanding of cosmic expansion may need fundamental revision. The universe may be more complex and surprising than current models predict. It's normal if this feels abstract. Physics often lives beyond intuition. The scales involved are so far removed from human experience that even trained cosmologists struggle to develop genuine intuitive understanding. We can perform calculations, create models, and make predictions, but the actual magnitude of cosmic distance remains something we approach intellectually rather than experientially. The composition of space itself challenges our understanding of what exists at cosmic scales. The familiar matter that forms stars, planets, and people represents only about 5% of the universe's total content. Dark matter, invisible but gravitationally influential, comprises roughly 27%. Dark energy, even more mysterious, makes up approximately 68%. This means that 95% of the universe consists of components we cannot directly observe and do not fully understand. Dark matter creates the gravitational scaffolding around which visible matter clusters. Computer simulations show that without dark matter, galaxies would not have formed, and the cosmic web would not exist. Yet this crucial component of reality interacts so weakly with ordinary matter that it passes through our bodies by the billions every second without any detectable effect. Dark energy appears to be a property of empty space itself. As the universe expands and creates more space, more dark energy comes into existence, driving accelerated expansion. This process has profound implications for cosmic scale over time. In the far future, expansion will carry all but our nearest galactic neighbors beyond the cosmic horizon. The observable universe will appear to contract, even as the actual universe grows ever larger. The relationship between quantum mechanics and cosmic scales reveals unexpected connections. The Planck length, approximately 10 to the minus 35 meters, represents the smallest scale at which our current understanding of physics remains valid. At the opposite extreme, the observable universe spans roughly 10 to the 26 meters. This represents about 60 orders of magnitude between the smallest and largest scales we can meaningfully discuss. Humans exist roughly in the middle of this cosmic size hierarchy, being enormous compared to fundamental particles, yet infinitesimally small compared to cosmic structures. This positioning isn't coincidental. Conscious observers may only be possible within a narrow range of scales where complex chemistry can occur while remaining small enough compared to cosmic structures that stable environments can persist. Recent mathematical explorations have uncovered potential relationships connecting quantum and cosmic scales. Some calculations suggest that the ratio of an electron's mass to the Planck mass, raised to a certain power, approximately equals the ratio of the Planck length to the observable universe's size. These connections hint at underlying principles that govern reality across all scales, suggesting that quantum mechanics and cosmology may be more fundamentally interconnected than previously understood. The concept of cosmic inflation provides insight into how the universe achieved its current scale from an initial state smaller than an atomic nucleus. During the first fraction of a second after the Big Bang, space expanded exponentially, growing by a factor of at least 10 to the 26th in less than 10 to the minus 32 seconds. This brief period of exponential growth stretched quantum fluctuations to cosmic scales, creating the density variations that eventually became galaxies and galaxy clusters. Without inflation, the universe would not have achieved the remarkable uniformity observed in the cosmic microwave background. Regions now separated by billions of light years would never have been in thermal contact, yet they show nearly identical temperatures. Inflation explains this by proposing that these regions were once close together before being stretched beyond each other's horizons. The inflationary paradigm also suggests that our observable universe represents only a tiny patch of a much larger, inflated space. Different regions may have experienced different amounts of inflation or may have inflated at different times, potentially creating a multiverse of cosmic domains with varying properties. Some theories propose that inflation is eternal, continuously creating new cosmic regions throughout an infinite expanse. These ideas push a cosmic scale beyond even the observable universe into realms of speculation where different regions of space might operate under different physical laws. The multiverse concept represents perhaps the ultimate extension of scale, proposing that what we call the universe is actually just one bubble in an infinite collection of cosmic domains. Current observations cannot directly test multiverse theories, as other cosmic domains would lie forever beyond our observational horizon. Yet the mathematical frameworks that successfully describe our observable universe naturally lead to multiverse predictions. This creates a profound question about the nature of scientific knowledge itself. How do we study aspects of reality that are fundamentally unobservable? The future evolution of cosmic scale will be shaped by the ongoing acceleration of expansion. As dark energy continues to drive space apart, our cosmic horizon will eventually begin to shrink. Galaxies beyond our local group will fade from view as their light becomes too redshifted to detect. In the far future, observers will see a much smaller, emptier universe, unaware of the vast cosmic architecture that once filled the sky. This temporal perspective reveals that our current view of the universe represents a unique moment in cosmic history. We exist during an epoch when the large-scale structure remains visible and mappable. Future civilizations, if any arise, will inhabit a lonelier cosmos where the evidence for the Big Bang and cosmic evolution may be much harder to discover. As we've seen, the universe operates on scales that consistently exceed human intuition and challenge our most fundamental assumptions about space, time, and existence itself. The observable universe represents just the beginning of cosmic scale, a finite window into what may be an infinite expanse. Beyond our cosmic horizon lies the great unknown, forever hidden yet potentially infinite in extent. Human beings evolved to understand distances measured in steps and throws, territories bounded by hills and rivers. Yet through careful observation and mathematical reasoning, we've learned to map structures spanning billions of light years and to contemplate scales that stretch toward infinity. This represents perhaps our species' greatest intellectual achievement, the ability to comprehend, however imperfectly, our place within the vast cosmic architecture that surrounds us. The scale physics can't show you isn't just a matter of larger numbers or more distant objects. It's the recognition that reality operates on levels that transcend human experience entirely, where our most basic intuitions about space and time begin to fail, and where the familiar concepts of near and far, large and small, lose their comfortable meanings in the face of cosmic immensity. If this idea stayed with you, you may want to explore next. What happens at the edge of space? The physics of cosmic boundaries. Yet the observable universe, vast as it is, represents only the beginning of cosmic scale. What we can see may be less than 1% of what actually exists. Current models suggest that if space is flat, which observations increasingly support, then the universe extends infinitely in all directions. An infinite universe would mean that beyond our cosmic light sphere, every possible arrangement of matter exists somewhere, repeated endlessly across space. This isn't speculation about what might be possible. It's a mathematical consequence of infinite space combined with a finite number of ways that matter and energy can arrange themselves within any given volume. In an infinite universe, there would be regions identical to our observable cosmos down to the quantum level. Not similar regions, identical ones. The atoms in your body, the thoughts in your mind, the words you're hearing right now, all repeated infinitely throughout space. the implications stretch beyond comfortable human thinking. Somewhere in an infinite universe, there exists a perfect copy of Earth where everything happened exactly as it did here, except you chose differently at one crucial moment. Somewhere else, the laws of physics might be subtly different, allowing for matter configurations impossible in our region. The infinite contains not just everything that did happen, but everything that could happen. Yet we can never observe these distant realms. They lie forever beyond our cosmic horizon, separated not just by distance, but by the fundamental structure of space-time itself. The speed of light creates an absolute boundary around what we can know. Information cannot travel faster than light, and space has been expanding for only a finite time since the Big Bang. This creates our observational prison, a sphere of knowledge surrounded by infinite mystery. Consider what this means for the very concept of cosmic scale. When we speak of the universe being 93 billion light-years across, we're describing only our local observable patch. The actual universe may be hundreds of times larger, thousands of times larger, or infinitely larger. Recent theoretical estimates suggest that space extends at least 250 times beyond our observable horizon, making the universe at least 7 trillion light-years in diameter. But even this staggering number may represent only a tiny fraction of cosmic reality. The multiverse concept pushes these ideas even further into realms that challenge the foundations of scientific thinking. Some theories propose that our universe is one bubble in an infinite collection of cosmic domains, each with potentially different physical laws and constants. In eternal inflation models, space continues expanding exponentially in most regions, occasionally spawning new universe bubbles, like ours where inflation ends and matter can form. These ideas emerge naturally from well-established physics rather than philosophical speculation. The same equations that accurately describe cosmic microwave background observations and Big Bang nucleosynthesis lead inevitably to multiverse predictions. Yet the multiverse remains forever unobservable, raising profound questions about the nature of scientific knowledge itself. As you contemplate these scales, notice how your mind struggles to hold them. The numbers become abstract symbols rather than meaningful quantities. This isn't a failure of imagination, it's an encounter with the fundamental limits of human cognition. We evolved to understand distances we could walk, time periods we could experience, quantities we could count. The universe operates on scales that render these evolved capabilities completely inadequate. The hierarchy of cosmic structures reveals this scaling challenge across multiple levels. Planets orbit stars across millions of kilometers. Stars cluster into galaxies spanning hundreds of thousands of light-years. Galaxies group into clusters stretching tens of millions of light-years. Clusters organize into superclusters hundreds of millions of light-years across. Superclusters arrange along filaments that span billions of light-years, separated by vast cosmic voids. Our local supercluster, called Laniakea, contains over 100,000 galaxies spread across 520 million light-years. The name means immeasurable heaven in Hawaiian, reflecting both the structure's enormous scale and our difficulty comprehending it. Laniakea itself represents just one node in the cosmic web, a small feature within larger structures that stretch across billions of light years. The cosmic web resembles a three-dimensional spider web or neural network with galaxies arranged along thin filaments surrounding enormous empty regions called voids. The largest voids span hundreds of millions of light years, containing virtually no galaxies. If you could somehow travel to the center of the largest known void, the nearest significant galaxy would be over 1 billion light years away. The night sky would be almost completely dark, with only the cosmic microwave background radiation providing any illumination. This web-like structure emerged from tiny quantum fluctuations in the early universe, amplified by billions of years of gravitational evolution. Computer simulations can reproduce the cosmic web's overall architecture, but the largest observed structures push the boundaries of what current models can explain. Some galaxy filaments are so large that light takes billions of years to cross them, raising questions about how gravity could coordinate structure formation across such vast scales. The measurement of these cosmic distances reveals the ingenious methods astronomers have developed to map space across impossible scales. For nearby objects, direct parallax measurements work, observing how stars appear to shift position as Earth orbits the Sun. But this technique fails beyond a few thousand light years, requiring increasingly indirect methods. Cepheid variable stars serve as cosmic lighthouses, pulsating with periods directly related to their intrinsic brightness. By measuring how bright these stars appear versus how bright they should be, astronomers can calculate distances across millions of light years. Type Ia supernovae, stellar explosions that reach predictable peak brightnesses, extend this cosmic distance ladder to billions of light years. For the most distant objects, redshift becomes the primary tool. As space expands, it stretches light wavelengths, shifting them toward the red end of the spectrum. The amount of redshift indicates how much space has expanded since the light was emitted, providing a measure of distance. Recent surveys have mapped millions of galaxies using this technique, creating three-dimensional maps of cosmic structure across unprecedented volumes. Yet each measurement technique introduces uncertainties that accumulate with distance. Our knowledge of the universe's largest scales carries significant error bars. Recent observations have revealed troubling discrepancies between different measurement methods, suggesting our understanding of cosmic expansion may need fundamental revision. The Hubble constant, which describes the current rate of cosmic expansion, shows different values depending on how it's measured. Local measurements using supernovae and Cepheid stars give one result, while observations of the cosmic microwave background give another. This tension has persisted despite increasingly precise measurements, suggesting that our standard model of cosmology may be incomplete. Recent observations by the Dark Energy Spectroscopic Instrument have mapped over 6 million galaxies across 11 billion years of cosmic history, providing the most detailed map of cosmic structure ever created. These measurements achieve statistical confidence levels that challenge standard assumptions about dark energy behavior, suggesting that the mysterious force driving cosmic acceleration may be more complex than previously thought. The composition of space itself adds another layer of mystery to cosmic scale. The matter we can see, all the stars, galaxies, and gas clouds, represents only about 5% of the universe's total content. Dark matter, invisible but gravitationally influential, comprises roughly 27%. Dark energy, even more mysterious, makes up approximately 68%. This means that 95% of the universe consists of components we cannot directly observe and do not fully understand. Dark matter provides the gravitational scaffolding around which visible matter clusters, creating the cosmic web's architecture. Without dark matter, galaxies would not have formed, stars would not have ignited, and planets would not exist. Dark energy appears to be a property of empty space itself, driving the acceleration of cosmic expansion. As space expands and creates more volume, more dark energy comes into existence, creating a feedback process that ensures expansion will continue accelerating forever. This has profound implications for the future evolution of cosmic scale. In the far future, cosmic expansion will carry all but our nearest galactic neighbors beyond the cosmic horizon. The observable universe will appear to shrink, even as the actual universe grows ever larger. Future astronomers will look out and see a much emptier cosmos, with little evidence of the Big Bang or cosmic evolution that we can observe today. You don't need to fully understand these dark components to appreciate their significance for cosmic scale. They represent the humbling recognition that most of reality remains hidden from direct observation. The universe we see through telescopes, magnificent as it appears, represents only the visible tip of a vast cosmic iceberg. The temporal dimension of cosmic observation creates another layer of complexity in understanding universal scale. When we look across space, we're simultaneously looking back through time. Light from the Andromeda galaxy left that galaxy 2.5 million years ago, showing us how it appeared when early human ancestors first walked the Earth. The cosmic microwave background, the afterglow of the Big Bang, represents the oldest light we can detect. This radiation was emitted when the universe was only 380,000 years old, providing a snapshot of cosmic conditions from an era when the first atoms were just beginning to form. The matter that emitted this ancient light has in the intervening time condensed into galaxies now calculated to be roughly 46 billion light-years away. This creates a four-dimensional perspective on cosmic scale, where distance and time become inseparable. The edge of the observable universe represents not just the farthest place we can see, but the earliest time we can observe. Beyond this boundary lies not just distant space, but also earlier epochs in cosmic history that remain forever inaccessible. The relationship between quantum mechanics and cosmic scales reveals unexpected connections that challenge our understanding of how the universe's smallest and largest features relate. The Planck length, approximately 10 to the minus 35 meters, represents the smallest scale at which our current understanding of physics remains valid. At this scale, space and time themselves may become granular, losing their smooth character. Recent mathematical explorations have uncovered intriguing relationships connecting quantum and cosmic scales. Some calculations suggest that fundamental ratios involving particle masses and the cosmic scale length are related in ways that hint at deeper underlying principles. These connections suggest that quantum mechanics and cosmology may be more fundamentally interconnected than previously understood. The inflationary paradigm provides insight into how quantum fluctuations became cosmic structures. During the first fraction of a second after the Big Bang, space expanded exponentially, stretching quantum uncertainty fluctuations to astronomical scales. These stretched fluctuations became the density variations that eventually evolved into galaxies and galaxy clusters. Inflation explains why the cosmic microwave background appears so uniform across the entire observable universe. Regions now separated by billions of light years were once in thermal contact before being stretched beyond each other's horizons. This process also suggests that our observable universe represents only a tiny patch of a much larger, inflated space. Different regions may have experienced different amounts of inflation, creating a multiverse of cosmic domains with varying properties. Some theories propose that inflation is eternal, continuously creating new cosmic regions throughout an infinite expanse. These ideas push the concept of cosmic scale into realms where different regions of space might operate under different physical laws. The future evolution of cosmic scale will be shaped by dark energy's continued influence. Current models predict that cosmic expansion will accelerate indefinitely, eventually carrying distant galaxies beyond our observational horizon. In roughly 100 billion years, only our local group of galaxies will remain visible, held together by gravity against cosmic expansion. This temporal perspective reveals that our current view of the universe represents a unique epoch in cosmic history. We exist during a golden age of cosmic observation, when the large-scale structure remains visible and mappable. Future civilizations, if any arise, will inhabit a much lonelier cosmos, where evidence for cosmic evolution may be difficult to discover. The tools and techniques astronomers use to probe cosmic scale continue evolving, revealing new layers of complexity with each improvement in observational capability. Gravitational wave detectors have opened an entirely new window on the universe, allowing us to observe cosmic events invisible to traditional telescopes. These ripples in space-time itself carry information about black hole mergers, neutron star collisions, and potentially the earliest moments of cosmic history. As detector sensitivity improves, gravitational waves may eventually provide access to cosmic scales and epochs currently beyond electromagnetic observation. The early universe, opaque to light, may have been transparent to gravitational waves, offering a potential probe of conditions during the first moments after the Big Bang. Space-based telescopes planned for the coming decades will map cosmic structure with unprecedented precision, potentially resolving current mysteries about dark energy and cosmic expansion. These observations may reveal whether our understanding of cosmic scale needs fundamental revision, or whether the universe holds additional surprises beyond current theoretical frameworks. It's normal if contemplating these scales produces a sense of vertigo or disorientation. The universe operates on levels that consistently exceed human intuition, where familiar concepts of near and far, large and small, lose their comfortable meanings. We're exploring territories where mathematics becomes our only reliable guide, and where the most basic questions about existence remain open. The recognition that observable reality may represent less than 1% of what exists should inspire both humility and wonder. Human beings, evolved to understand distances measured in footsteps and territories bounded by horizons, have somehow learned to contemplate scales that stretch toward infinity. This represents perhaps our species' most remarkable intellectual achievement, the ability to transcend our evolutionary limitations and glimpse, however imperfectly, the vast cosmic architecture that surrounds us. Yet with each new discovery, the universe reveals additional layers of complexity and mystery. The scale physics can't show you isn't just a matter of larger numbers or more distant objects. It's the recognition that reality operates on levels that transcend direct human experience, where our most sophisticated instruments reveal only fragments of a cosmic puzzle whose complete picture may forever remain beyond our grasp. The universe maintains its secrets even as it reveals its wonders. Each answer leads to deeper questions. Each measurement exposes new mysteries. Each glimpse of cosmic architecture hints at even grander structures lying just beyond our observational reach. In confronting the true scale of cosmic reality, we encounter not just the limits of human knowledge, but the endless depth of existence itself. If this idea stayed with you, you may want to explore next. What lives in the space between galaxies? The hidden universe of cosmic voids. The question of what lies beyond our cosmic horizon leads us into territories where language itself begins to fail. We speak of cosmic boundaries, but boundaries imply something on the other side. We discuss the edge of the observable universe, but edges suggest surfaces that can be approached and crossed. The reality is stranger and more subtle than these familiar concepts allow. Imagine standing at the shore of an ocean that extends beyond every horizon. You can see perhaps 20 kilometers to where the curve of the Earth carries the surface beyond your view. But unlike Earth's oceans, which have distant shores and measurable depths, the cosmic ocean may have no far side at all. The boundary of observation isn't a place you could travel to. It's a limit imposed by time itself, by the finite age of the universe and the absolute speed of light. This creates what cosmologists call the Hubble sphere, a region beyond which galaxies recede faster than light can travel toward us. Objects crossing this boundary don't disappear instantly. Their light, already en route, continues reaching us for billions of years. But no new information from those regions can ever arrive. They slip gradually from observable to unobservable, like ships sailing beyond the horizon in slow motion. As you contemplate this, notice how your intuition rebels against the concept. Your mind wants to ask what lies beyond the boundary, what you would see if you could somehow travel there. But these questions assume a perspective that doesn't exist. There is no outside vantage point from which to observe the universe's edge. There is no external reference frame that could contain both observer and observed. The mathematics of cosmic expansion reveals something even more unsettling about the future of observation. Current models predict that our cosmic horizon will eventually begin to shrink. As space continues expanding at an accelerating rate, distant galaxies will cross the boundary from observable to unobservable. Not because they're destroyed or hidden, but because their light becomes too stretched and redshifted for any conceivable detector to register. This process has already begun. The most distant galaxies we can observe today are receding at roughly 90% the speed of light. Their light, stretched by billions of years of cosmic expansion, arrives as faint infrared radiation that pushes our most sensitive instruments to their limits. In a few billion years, these galaxies will fade beyond detectability, their final photons arriving so redshifted and diluted that they blend into the cosmic microwave background itself. Consider what this means for the concept of cosmic knowledge. Future astronomers will inhabit a universe that appears progressively smaller and emptier. Eventually, only our local group of galaxies will remain visible, held together by gravity against the cosmic expansion. These future observers will look out and see a cosmos containing perhaps a few dozen galaxies surrounded by apparent emptiness. They'll have no direct evidence for the Big Bang, no cosmic microwave background radiation to study, no distant supernovae to measure cosmic acceleration. The rich tapestry of cosmic evolution that we can observe today will have faded beyond their reach. They'll inhabit a universe that appears static and eternal, unaware that they're seeing only the remnants of a once magnificent cosmic architecture. This temporal perspective on cosmic scale reveals something profound about the nature of knowledge itself. What we can know about the universe depends not just on our location in space, but on our position in cosmic time. We exist during a unique epoch when the evidence for cosmic evolution remains visible and interpretable. Earlier in cosmic history, the universe was opaque to light. Later, it will appear nearly empty. Our moment represents a brief window of cosmic transparency. The realization that knowledge has temporal boundaries extends beyond simple observational limits. The very questions we can ask about the universe depend on the cosmic context we inhabit. Future civilizations, if they arise, will face fundamentally different mysteries than those that occupy us today. They'll develop theories to explain a cosmos that appears to contain only local galaxies, perhaps never suspecting the vast architecture that once filled the sky. You don't need to find this comforting or disturbing. It simply is. The universe operates according to physical laws that create natural boundaries around what can be known from any particular vantage point. These limits aren't failures of science or technology. They're consequences of the fundamental structure of space-time itself. The study of cosmic voids provides another perspective on scale that challenges conventional thinking about space and structure. These enormous empty regions, some spanning hundreds of millions of light years, contain virtually no galaxies. If you could somehow find yourself in the center of the largest known void, the nearest significant galaxy would be over 1 billion light years away. The night sky from such a location would be profoundly different from anything humans have ever experienced. Instead of thousands of visible stars, you might see only a handful of distant points of light. The Milky Way, Andromeda, and all the familiar constellations would be invisible, lost in the glare of the single dwarf galaxy that happened to share your local void. The cosmic microwave background radiation would provide virtually the only evidence that a larger universe existed beyond the darkness. These voids aren't truly empty. They contain dark matter, forming an invisible scaffolding that shapes their boundaries. Occasionally, a galaxy forms within them, but these isolated island universes evolve differently than galaxies in denser regions. They experience less interaction, fewer mergers, and different star formation histories. In some sense, they represent alternative evolutionary paths for cosmic structure. The existence of such voids challenges our understanding of how structure formation occurs on cosmic scales. Computer simulations can reproduce the overall web-like pattern of cosmic architecture, but the largest voids push against theoretical limits. Some are so empty and so large that it's difficult to explain how gravity could have evacuated them so thoroughly within the time available since the Big Bang. Recent observations have revealed that these voids aren't completely static. They're expanding faster than the average cosmic expansion, growing larger as dark energy pushes their boundaries outward. This creates a feedback process where large voids grow larger while dense regions become denser. The cosmic web is becoming more pronounced over time, with starker contrasts between the filaments where galaxies cluster and the voids where almost nothing exists. The largest known void, discovered in 2007, spans approximately 1.8 billion light-years across. To put this in perspective, if our local supercluster were placed at one edge of this void, the Andromeda Galaxy would appear as a barely detectable smudge at the limit of telescopic visibility. The void is so large that light takes nearly 2 billion years to cross from one side to the other. Such scales strain not only human comprehension, but also current theoretical frameworks. The void is larger than many models predicted should be possible, given the age of the universe and the known properties of dark matter and dark energy. Its existence suggests that cosmic structure formation may be more complex and varied than standard theories account for. As you listen, notice how these void scales make even galactic distances feel intimate. The 100,000 light-years across our galaxy, which seemed impossibly vast when considered alone, becomes a negligible speck when placed within cosmic voids. This recursive scaling, where each larger context makes the previous one feel small, continues throughout cosmic architecture without apparent end. The study of cosmic topology raises questions about the shape of space itself on the largest scales. While space appears flat in our local region, the global geometry of the universe remains uncertain. Current observations are consistent with infinite flat space, but they cannot rule out more subtle geometries that would only become apparent across distances much larger than our observable horizon. If space has a complex topology, traveling in what appears to be a straight line might eventually return you to your starting point, like sailing around a sphere. In such a universe, sufficiently powerful telescopes might observe the same galaxies appearing in multiple directions, showing them at different epochs in their evolution. Some cosmologists have searched for such repetitions in cosmic microwave background data, but none have been definitively identified. The possibility of cosmic topology introduces another layer of mystery to the question of scale. Even if space is infinite, it might have a shape that creates unexpected connections between distant regions. In a toroidal universe, for instance, space might be finite in volume but have no edges or boundaries. Travelers could journey forever without reaching any limit, yet the total amount of space would be finite. These topological possibilities remind us that our intuitions about space, shaped by everyday experience with Euclidean geometry, may fail completely when applied to cosmic scales. The universe might have properties that remain forever hidden from local observation, geometric features that only become apparent across distances far exceeding our observational reach. The relationship between cosmic scale and fundamental physics reveals connections that stretch across the entire hierarchy of natural phenomena. The same quantum fluctuations that operate at subatomic scales provided the seeds for cosmic structure formation. These tiny variations, amplified by inflation and shaped by billions of years of gravitational evolution, became the galaxies and galaxy clusters we observe today. This connection between the infinitesimally small and the cosmically large suggests that understanding either domain requires knowledge of the other. Particle accelerators probe quantum interactions that occurred during the first moments of cosmic history. Cosmic observations test theories about fundamental forces and particles that cannot be directly studied in laboratory conditions. Recent mathematical work has uncovered intriguing relationships connecting quantum and cosmic parameters. Some calculations suggest that certain ratios involving fundamental constants appear at both microscopic and macroscopic scales in ways that hint at deeper organizational principles. These connections remain largely mysterious, but they suggest that the apparent separation between quantum and cosmic physics may be more artificial than fundamental. The precision with which these relationships hold across such vastly different scales raises profound questions about the nature of physical law itself. Why should ratios involving electron masses and nuclear scales be mathematically related to ratios involving cosmic expansion and galaxy formation? These connections might be coincidental, but they might also reflect underlying principles that govern reality across all scales. Current theories attempt to unify quantum mechanics and general relativity into a single framework that could explain these cross-scale relationships. String theory, loop quantum gravity, and other approaches propose that space and time themselves might have quantum properties that only become apparent under extreme conditions or across cosmic scales. If such theories prove correct, they might reveal that the separation between small and large, quantum and cosmic, represents a limitation of current understanding rather than a fundamental feature of reality. The universe might operate according to principles that naturally connect its smallest and largest scales in ways that current physics can only glimpse. You don't need to understand these theoretical connections to appreciate their significance for cosmic scale. They suggest that the universe operates as an integrated system where events at every scale influence and reflect events at every other scale. This holistic perspective transforms questions about cosmic size into questions about the fundamental nature of existence itself. The future of cosmic observation will depend on technologies that can probe scales currently beyond our reach. Gravitational wave detectors have already opened new windows on the universe, revealing cosmic events invisible to traditional telescopes. As these instruments become more sensitive, they may detect signals from the early universe that carry information about cosmic structure formation on previously inaccessible scales. Space-based interferometers planned for the coming decades will be sensitive to gravitational waves with wavelengths comparable to the size of the solar system. These enormous ripples in space-time could carry information about supermassive black hole mergers, cosmic string networks, and potentially the inflationary epoch itself. Such observations might reveal whether space has discrete properties at the smallest scales, whether cosmic inflation actually occurred, and whether our universe is one of many in a larger multiverse structure. They could provide direct tests of quantum gravity theories and reveal new physics operating at the intersection of cosmic and quantum scales. Other planned observatories will map cosmic structure with unprecedented precision, potentially resolving current puzzles about dark matter and dark energy. These surveys might reveal whether cosmic acceleration is truly constant or varies over time and distance. They could uncover new types of cosmic structures or confirm that our current understanding accurately describes reality on the largest observable scales. As these capabilities develop, they may push the boundaries of cosmic observation closer to fundamental limits imposed by the quantum nature of space-time itself. At some point, further improvements in precision might reveal that space and time have discrete rather than continuous properties, opening entirely new domains of physics that bridge quantum and cosmic scales. It's normal if contemplating these future possibilities produces a sense of both excitement and uncertainty. The universe continues revealing new layers of complexity with each improvement in observational capability. Every answer leads to deeper questions. Every measurement exposes new mysteries. Every glimpse of cosmic architecture hints at even grander structures lying just beyond our current reach. The recognition that we exist during a unique epoch of cosmic observability should inspire both urgency and humility. The universe's large-scale structure remains visible and mappable today, but this transparency will gradually fade as cosmic expansion carries distant regions beyond our observational horizon. Future generations may inhabit a cosmos that appears much smaller and emptier than the rich architectural complexity we can study today. Yet even as observable reality shrinks, the actual universe continues growing larger and more complex. Dark energy ensures that cosmic expansion will accelerate indefinitely, creating ever more space while carrying matter and energy into increasingly dilute configurations. The universe's far future stretches across timescales that dwarf its current age, promising eons of evolution that we can barely begin to imagine. In confronting the true scale of cosmic reality, we encounter not just the vastness of space and time, but the profound depths of our own ignorance. Each measurement reveals how much more remains unknown. Each discovery opens new territories of mystery. Each glimpse of cosmic truth exposes the vast territories that lie beyond our understanding. The universe maintains its secrets, even as it reveals its wonders. The scale physics can't show you represents not just a limitation of current knowledge, but an invitation to continue exploring, to keep pushing against the boundaries of what can be known, to remain humble before the infinite complexity that surrounds us. The cosmos operates on levels that consistently exceed human intuition and challenge our most basic assumptions about the nature of existence. In learning to contemplate these scales, we discover not just the size of the universe, but the remarkable capacity of human consciousness to transcend its evolutionary origins and glimpse, however briefly and imperfectly, the vast architecture within which we find ourselves embedded. These moments of cosmic perspective carry their own quiet power. They remind us that despite our apparent insignificance within the larger scheme, we represent something remarkable. Matter, organized into patterns capable of contemplating its own cosmic context. Conscious observers who can measure distances they could never travel and comprehend scales they could never directly experience. The universe, vast and indifferent as it may be to human concerns, has nonetheless produced within itself the capacity for understanding. In contemplating cosmic scale, we participate in the universe's ongoing process of coming to know itself. This represents, perhaps, the most profound aspect of cosmic scale, not just its enormous size, but its ability to generate within tiny, isolated pockets of space and time the awareness necessary to comprehend its own vastness. If this idea stayed with you, you may want to explore next. What happens when galaxies die? The physics of cosmic endings. The study of cosmic horizons reveals layers of mystery that extend far beyond simple questions of distance. Each type of horizon represents a different kind of boundary, not in space, but in the very nature of what can be known. The particle horizon marks the limit of regions that could have ever influenced us since the Big Bang. The event horizon delineates regions we can influence in the future, and the Hubble horizon shows where space itself expands faster than light can traverse it. These boundaries shift and evolve as the universe ages. Objects that cross from observable to unobservable don't vanish instantly. Their final photons continue arriving for billions of years, growing progressively redder and fainter until they merge indistinguishably with the cosmic microwave background itself. We're witnessing a gradual fade rather than an abrupt cutoff, like watching ships disappear over a horizon in extreme slow motion. The mathematics reveal something unsettling about cosmic communication. Beyond a certain distance, roughly 16 billion light years away, any signal we transmit today will never reach its destination. Space expands so rapidly in those regions that our fastest possible message, traveling at light speed, makes no progress against the cosmic current. These regions slip permanently beyond our causal influence, creating isolated islands of space-time that can never again exchange information. As you contemplate this, notice how the concept challenges fundamental assumptions about connection and communication. On human scales, any 2 points can theoretically be connected if we're willing to wait long enough or travel far enough. But cosmic expansion creates absolute separations that no amount of time or technology can bridge. The universe naturally fragments into causally disconnected domains. Consider what this means for any civilizations that might exist in those unreachable regions. They inhabit a universe that includes us, just as ours includes them, yet we exist in permanent isolation. Their light reaches us from the distant past, but no signal we send today will ever arrive at their current location. We share the same cosmos, while remaining forever unable to communicate. Recent observations have begun mapping these cosmic horizons with unprecedented precision. The Dark Energy Spectroscopic Instrument has charted the positions and redshifts of over 6 million galaxies, creating the most detailed three-dimensional map of cosmic structure ever assembled. This survey reveals galaxies approaching the observational boundary, their light stretched to the very limits of detectability. The data suggests that our understanding of cosmic expansion may need revision. Standard models predict that dark energy should remain constant over time, but the observations show subtle variations that challenge this assumption. Dark energy appears to evolve, growing stronger or weaker across cosmic history in ways that current theories struggle to explain. These measurements achieve statistical confidence levels that rule out constant dark energy behavior with extraordinary certainty. The probability that these variations result from measurement error is less than 1 in 30,000. Something fundamental about cosmic expansion appears to be more complex than our best models predict. You don't need to understand the technical details to appreciate what this means for cosmic scale. The universe may be expanding in ways that will affect how rapidly distant regions slip beyond our horizon. If dark energy strengthens over time, the observable universe will shrink faster than predicted. If it weakens, we might retain access to distant regions longer than expected. The study of cosmic structure formation reveals how small quantum fluctuations became the vast architecture we observe today. During cosmic inflation, uncertainty principle variations in vacuum energy were stretched to astronomical scales. These stretched fluctuations became the density variations that eventually evolved into galaxies, galaxy clusters, and the cosmic web itself. Computer simulations can reproduce this process across billions of years of cosmic evolution. They begin with the nearly uniform conditions revealed by cosmic microwave background observations and apply the known laws of gravity and gas dynamics. The results match observed cosmic structure with remarkable accuracy, confirming our understanding of how tiny quantum seeds became cosmic architecture. Yet the largest observed structures push against theoretical limits. Some galaxy filaments and supervoids are so massive that it's unclear how they could have formed within the time available since the Big Bang. The Hercules Corona Borealis Great Wall stretches across 10 billion light-years, requiring coordinated structure formation across distances so vast that different regions could never have exchanged information. The cosmic web itself displays properties that challenge conventional thinking about structure formation. Galaxies arrange along thin filaments surrounding enormous voids in patterns that resemble neural networks or soap foam. This organization emerges naturally from gravitational evolution, but the mathematical principles governing its emergence remain incompletely understood. Dark matter provides the gravitational scaffolding for all cosmic structure, yet its nature remains completely mysterious. This invisible component comprises roughly 27% of the universe's total content, outweighing ordinary matter by more than 5 to 1. Without dark matter's gravitational influence, galaxies would never have formed, and stars would never have ignited. Current theories propose that dark matter consists of undiscovered subatomic particles that interact only through gravity. These particles would permeate all of space, including the room where you're listening, passing through your body by the billions every second without any detectable effect. Their presence shapes cosmic architecture while remaining completely invisible to electromagnetic radiation. Underground detectors have searched for dark matter particles for decades without definitive success. These experiments use increasingly sensitive techniques to catch hypothetical dark matter particles colliding with ordinary atoms, but the interactions prove so rare and subtle that they remain at the edge of detectability. The universe's dominant component continues eluding direct observation. Alternative theories propose that dark matter effects might result from modifications to gravity itself rather than unknown particles. These approaches suggest that gravitational attraction strengthens under certain conditions in ways that mimic additional invisible mass. Such theories face their own challenges in explaining all observed phenomena, but they demonstrate that fundamental questions about cosmic structure remain open. As you listen, notice how these mysteries accumulate rather than resolve. Each answer about cosmic scale leads to deeper questions about the nature of space, time, matter, and energy. The universe reveals its architecture while concealing the principles that govern its construction. The temporal dimension of cosmic observation adds another layer of complexity to questions about scale and structure. When we map distant galaxies, we're creating a four-dimensional picture that captures their positions across both space and cosmic time. Light from the most distant observable objects has been traveling for over 13 billion years, showing us cosmic conditions from when the universe was less than 1 billion years old. These early galaxies appear smaller, more irregular, and more actively star-forming than their modern counterparts. They represent different stages in cosmic evolution, showing how structure develops and matures over billions of years. The universe grows more organized over time as small galaxies merge into larger ones and gas settles into stable rotating disks. Yet this temporal perspective creates puzzles about cosmic evolution. Some early galaxies appear more massive and mature than current models predict should be possible at such early epochs. They seem to have assembled too quickly, forming complex structures before sufficient time had elapsed for normal gravitational processes to operate. Recent observations by the James Webb Space Telescope have revealed galaxies that existed when the universe was only a few 100 million years old. These ancient systems appear surprisingly large and organized, suggesting that cosmic structure formation may proceed faster than standard theories predict. The early universe might have been more dynamic and rapidly evolving than previously imagined. These discoveries force astronomers to reconsider fundamental assumptions about how cosmic structure emerges. The timeline of galaxy formation may need revision, requiring new physics or different initial conditions to explain how complex systems assembled so quickly after the Big Bang. The relationship between cosmic time and observable distance creates unique challenges for understanding universal scale. Objects at different distances appear at different epochs in cosmic history, making it impossible to create a snapshot of the entire universe at any single moment. Our view of cosmic structure necessarily spans billions of years of evolution. This temporal mixing means that questions about cosmic scale cannot be separated from questions about cosmic history. The universe's current size, structure, and composition all depend on its evolutionary trajectory since the Big Bang. Understanding scale requires understanding time, and understanding time requires understanding the physical processes that drive cosmic change. The study of cosmic acceleration reveals how dark energy affects the future evolution of scale and structure. Current observations show that cosmic expansion has been accelerating for approximately 5 billion years, driven by this mysterious component that appears to be a property of empty space itself. As space expands, it creates more volume, which contains more dark energy, which drives faster expansion in a self-reinforcing cycle. This feedback process ensures that cosmic acceleration will continue indefinitely, eventually dominating all other forces, except gravity within gravitationally bound systems. The implications for cosmic structure are profound. While dark energy cannot overcome the gravity that holds galaxies and galaxy clusters together, it prevents the formation of new, large-scale structures. The cosmic web has essentially frozen in its current configuration, with no new filaments or supervoids forming as space continues expanding. Over cosmic timescales, dark energy will gradually stretch the cosmic web until its filaments become so dilute that they effectively disappear. Galaxies within our local group will remain bound together, but all other structures will fade beyond the cosmic horizon as their light becomes too redshifted to detect. Models predict that in roughly 100 billion years, only our merged Milky Way Andromeda system and its satellite galaxies will remain observable. The rich cosmic architecture visible today will have faded into invisibility, leaving future astronomers with little evidence of the broader universe's existence. Yet even this local remnant will continue evolving. Stars will exhaust their fuel and fade over trillions of years. Stellar remnants will slowly evaporate through various quantum processes. Eventually, even the largest black holes will decay through Hawking radiation, leaving only elementary particles dispersed through ever-expanding space. You don't need to find these timescales comforting or disturbing. They represent the natural consequences of physical laws operating across cosmic time. The universe follows its own trajectory, regardless of human preferences or concerns. The recognition that we exist during a brief epoch of cosmic transparency should inspire neither urgency nor despair, but rather a quiet appreciation for the remarkable circumstances that make cosmic observation possible. We inhabit a universe old enough for complex structure to have formed, yet young enough for that structure to remain visible and mappable. Future developments in gravitational wave astronomy may provide new windows on cosmic scale that remain unaffected by electromagnetic horizons. These ripples in space-time itself travel at light speed but carry information about cosmic events that remain invisible to traditional telescopes. Planned space-based interferometers will detect gravitational waves with wavelengths comparable to planetary orbits, revealing supermassive black hole mergers from cosmic dawn. These observations might probe structure formation during epochs when the universe was opaque to light, providing direct access to cosmic evolution during previously unobservable periods. Gravitational waves from cosmic inflation itself might carry information about the universe's earliest moments, when quantum fluctuations were first stretched to cosmic scales. Such observations would provide direct tests of inflationary theory and potentially reveal whether our cosmos is one of many in a larger multiverse structure. As detection sensitivity improves, gravitational wave astronomy might eventually probe the quantum nature of space-time itself. At sufficiently small scales, space and time might have discrete, rather than continuous properties, creating subtle effects that accumulate over cosmic distances and times. These technological advances promise to extend our observational reach into previously inaccessible domains of cosmic scale and structure. Yet they also remind us that each new capability reveals additional layers of complexity and mystery that lie beyond our current understanding. The universe continues revealing new aspects of its architecture with each improvement in observational capability. Every answer leads to deeper questions. Every measurement exposes new puzzles. Every glimpse of cosmic truth points toward vast territories that remain unexplored. It's normal if contemplating these scales and timescales produces a sense of both wonder and vertigo. The universe operates according to principles that consistently exceed human intuition and challenge our most basic assumptions about the nature of existence itself. In learning to think about cosmic scale, we discover not just the size of the universe, but the remarkable capacity of human consciousness to transcend its evolutionary limitations. We represent something extraordinary, matter organized into patterns capable of contemplating cosmic architecture that extends far beyond any direct experience. The cosmos may be vast and indifferent to human concerns, but it has nonetheless produced within isolated pockets of space and time the awareness necessary to comprehend its own structure. This represents perhaps the most profound aspect of cosmic scale, not just its enormous extent, but its ability to generate the consciousness required to map its own vastness. These moments of cosmic perspective carry a quiet power that transcends mere intellectual understanding. They connect us to something larger than individual existence, while reminding us of our remarkable position as conscious observers embedded within the very architecture we're trying to comprehend. The universe maintains its mysteries even as it reveals its wonders. The scale physics can't show you represents not just a limitation of current knowledge, but an invitation to continue exploring the boundaries of what can be known about the cosmos that surrounds us. In confronting these scales, we encounter both the vastness of space and time and the profound depths of our own capacity for understanding. Each measurement pushes against the limits of what consciousness can grasp, yet somehow we continue finding ways to extend those limits and glimpse ever more distant territories of cosmic reality. The recognition that observable reality may represent only a tiny fraction of what exists should inspire not despair, but humility. We're explorers mapping territories whose full extent may forever exceed our reach. Yet the fragments we can observe reveal architecture of breathtaking complexity and beauty. The universe unfolds its secrets gradually, requiring patience and persistence to decode. Each generation of observers adds to our understanding while discovering new horizons that stretch toward infinity. This ongoing process of cosmic discovery represents one of humanity's most remarkable achievements: the ability to comprehend, however imperfectly, the vast architectural context within which we find ourselves embedded. If this idea stayed with you, you may want to explore next. What lies beyond the edge of time? The physics of cosmic beginnings. The concept of cosmic topology opens questions about the shape of space itself that extend far beyond what telescopes can reveal. Current observations show that space appears flat in our local region, but the global geometry of the universe remains fundamentally uncertain. We can measure angles and distances across billions of light years, yet these measurements tell us nothing about whether space curves back on itself across even larger scales. Imagine standing on what appears to be an endless flat plain. You could walk in any direction for days without encountering hills or boundaries. The ground beneath your feet would feel perfectly level, yet you might actually be standing on the surface of an enormous sphere, so large that its curvature remains imperceptible across any distance you could travel. The universe might have similar hidden geometries that only become apparent across scales vastly exceeding our observational reach. If space has complex topology, a photon traveling in what appears to be a straight line might eventually return to its point of origin, like a ship sailing around the Earth. In such a universe, sufficiently powerful telescopes might observe the same galaxies appearing in multiple directions, showing them at different stages of their evolution. Some cosmologists have searched for such repetitions in the cosmic microwave background, looking for matching patterns that would reveal space folding back on itself. These searches have found intriguing correlations, but nothing conclusive. The universe might be infinite and flat, as current data suggests, or it might be finite but so large that its topology remains hidden beyond our cosmic horizon. We exist within a cosmic bubble of knowledge, unable to determine whether space extends forever or eventually curves back to meet itself. The possibility that space has hidden geometry reminds us how local observations can mislead about global structure. Ancient navigators thought Earth was flat because they could only observe small patches of its surface. We might face similar limitations when trying to understand cosmic geometry. The universe's true shape might only become apparent across distances that dwarf even our vast observable region. As you contemplate this uncertainty, notice how it challenges basic assumptions about space itself. We think of distance as straightforward, of directions as absolute, of space as a simple container for objects. Yet these intuitions, perfectly reliable for everyday navigation, might completely misrepresent the nature of cosmic geometry. The study of dark energy reveals another layer of mystery about cosmic scale that operates beyond direct observation. This component comprises roughly 68% of the universe's total energy content, yet its nature remains completely unknown. It appears to be a property of empty space itself, causing cosmic expansion to accelerate over time. Recent observations suggest that dark energy might not be constant, as standard models assume. The Dark Energy Spectroscopic Instrument has mapped millions of galaxies across cosmic time, revealing subtle variations in cosmic acceleration that challenge theoretical predictions. These measurements achieve extraordinary statistical confidence, ruling out constant dark energy behavior with probabilities of error less than 1 in 30,000. If dark energy evolves over cosmic time, it transforms our understanding of the universe's future evolution. Current models predict that cosmic expansion will accelerate indefinitely, eventually carrying all but our nearest galactic neighbors beyond the observable horizon. But if dark energy weakens over time, this timeline might extend significantly. If it strengthens, the observable universe might shrink faster than predicted. The measurements hint at something more complex than a simple cosmological constant. Dark energy might be a dynamic field that changes properties as space expands and evolves. It might interact with matter and radiation in subtle ways that only become apparent across cosmic scales and time periods. The universe's dominant component remains as mysterious today as when it was first discovered. You don't need to understand the mathematical details to appreciate what this uncertainty means for cosmic scale. The very processes that determine how large the observable universe becomes, how quickly distant regions slip beyond our reach, and how cosmic structure evolves over time depend on physics we don't yet comprehend. The recognition that 95% of the universe consists of dark matter and dark energy creates a profound epistemological challenge. How do we study components of reality that remain invisible to all direct observation? Dark matter reveals itself only through gravitational effects on visible matter. Dark energy manifests only through cosmic acceleration measurements. Both components shape cosmic structure and evolution while remaining completely hidden from electromagnetic observation. This invisible majority means that the universe we see through telescopes represents only the visible tip of a vast cosmic iceberg. The galaxies, stars, and gas clouds that populate astronomical photographs account for less than 5% of cosmic reality. The remaining 95% operates according to principles we're only beginning to glimpse. Computer simulations reveal how dark matter creates the gravitational scaffolding for all cosmic structure. Without this invisible component, galaxies would never have formed, stars would never have ignited, and planets would never have condensed. The entire visible universe owes its existence to processes involving matter that remains completely undetectable except through its gravitational influence. Dark matter particles, if they exist, would permeate all of space, including the room where you're listening. Billions would pass through your body every second without any detectable interaction. They would provide the gravitational foundation for cosmic architecture while remaining completely transparent to electromagnetic radiation. Underground laboratories have searched for these hypothetical particles for decades, using increasingly sensitive detectors to catch rare collisions with ordinary atoms. The experiments probe interaction rates so low that they approach fundamental quantum limits. Yet despite extraordinary technical sophistication, dark matter particles continue eluding direct detection. Alternative theories propose that dark matter effects might result from modifications to gravity itself rather than unknown particles. These approaches suggest that gravitational attraction behaves differently under certain conditions, creating apparent effects that mimic additional invisible mass. Such theories face challenges in explaining all observed phenomena, but they demonstrate that fundamental questions about cosmic structure remain open. As you listen, notice how these mysteries accumulate rather than resolve. Each measurement reveals new aspects of cosmic architecture while exposing deeper layers of ignorance about the principles governing its construction. The universe reveals its structure while concealing the physics that creates that structure. The temporal dimensions of cosmic observation adds another layer of complexity to understanding scale and structure. Light from distant objects carries information about cosmic conditions from different epochs in universal history. When we map the observable universe, we're creating a four-dimensional picture that captures both spatial relationships and temporal evolution. The most distant observable galaxies appear as they existed when the universe was less than 1 billion years old. These early systems look different from modern galaxies, appearing smaller, more irregular, and more actively star-forming. They represent snapshots of cosmic youth, showing how structure develops and matures over billions of years. Recent observations by advanced telescopes have revealed galaxies that formed when the universe was only a few 100 million years old. These ancient systems appear surprisingly large and organized, suggesting that cosmic structure formation proceeded faster than standard theories predict. The early universe might have been more dynamic and rapidly evolving than previously imagined. These discoveries force reconsideration of fundamental assumptions about how cosmic architecture emerges. The timeline of galaxy formation may need revision, requiring new physics or different initial conditions to explain how complex systems assembled so quickly after the Big Bang. The relationship between cosmic time and observable distance creates unique challenges for understanding universal scale. Objects at different distances appear at different epochs in cosmic history, making it impossible to create a true snapshot of the entire universe at any single moment. Our view necessarily spans billions of years of evolution. This temporal mixing means that questions about cosmic scale cannot be separated from questions about cosmic history. Understanding the universe's current size, structure, and composition requires understanding its evolutionary trajectory since the Big Bang. Scale and time become inseparable aspects of cosmic reality. The study of cosmic voids provides another perspective on scale that challenges conventional thinking about space and structure. These enormous empty regions span hundreds of millions of light years while containing virtually no galaxies. If you could find yourself at the center of the largest known void, the nearest significant galaxy would be over 1 billion light years away. The night sky from such a location would be profoundly different from anything humans have experienced. Instead of thousands of visible stars, you might see only scattered points of distant light. The Milky Way, Andromeda, and all familiar constellations would be invisible, lost beyond the darkness. The cosmic microwave background radiation would provide virtually the only evidence that a larger universe existed beyond the void. These empty regions aren't truly empty. They contain dark matter, forming invisible scaffolding that shapes their boundaries. Occasionally, a galaxy forms within them, but these isolated systems evolve differently than galaxies in denser regions. They experience fewer interactions, different merger histories, and alternative paths of cosmic evolution. The existence of such vast voids challenges understanding of how structure formation occurs on cosmic scales. Computer simulations can reproduce the overall web-like pattern of cosmic architecture, but the largest voids push against theoretical limits. Some are so empty and so large that it's difficult to explain how gravity could have evacuated them so thoroughly within the time available since the Big Bang. Recent observations reveal that these voids aren't static. They're expanding faster than average cosmic expansion, growing larger as dark energy pushes their boundaries outward. This creates a feedback process where large voids become larger while dense regions grow denser. The cosmic web becomes more pronounced over time, with starker contrasts between galaxy-rich filaments and galaxy-poor voids. You don't need to visualize these scales precisely to appreciate their significance. They represent territories where the familiar concepts of near and far, empty and full, lose their comfortable meanings. Distance becomes something qualitatively different when measured across regions where galaxies are separated by billions of light years of nearly empty space. The largest known void spans approximately 1.8 billion light years across. Light takes nearly 2 billion years to cross from one side to the other. This void is so large that if our local supercluster were placed at one edge, familiar galaxies would appear as barely detectable smudges at the limits of telescopic visibility. Such scales strain not only human comprehension, but also current theoretical frameworks. The void's existence suggests that cosmic structure formation may be more complex and varied than standard models account for. The universe might have properties that only become apparent across distances that vastly exceed current observational capabilities. The relationship between quantum mechanics and cosmic scales reveals unexpected connections that bridge the smallest and largest domains of physics. The same quantum fluctuations that operate at subatomic scales provided the seeds for cosmic structure formation. These microscopic variations, amplified by inflation and shaped by billions of years of gravitational evolution, became the galaxies and galaxy clusters we observe today. This connection between infinitesimal and cosmic suggests that understanding either domain requires knowledge of the other. Particle accelerators probe quantum interactions that occurred during the universe's first moments. Cosmic observations test theories about fundamental forces and particles that cannot be directly studied in laboratory conditions. Recent mathematical work has uncovered intriguing relationships connecting quantum and cosmic parameters. Some calculations suggest that certain ratios involving fundamental constants appear at both microscopic and macroscopic scales in ways that hint at deeper organizational principles governing reality. The precision with which these relationships hold across vastly different scales raises profound questions about the nature of physical law itself. Why should ratios involving electron masses and nuclear scales be mathematically related to ratios involving cosmic expansion and galaxy formation? These connections might be coincidental, but they might also reflect underlying principles that govern the universe across all scales. Current theories attempt to unify quantum mechanics and general relativity into frameworks that could explain these cross-scale relationships. If such unification proves successful, it might reveal that the apparent separation between quantum and cosmic physics represents a limitation of current understanding rather than a fundamental feature of reality. As you contemplate these connections, notice how they challenge conventional thinking about scale itself. The universe might operate as an integrated system where events at every scale influence and reflect events at every other scale. This holistic perspective transforms questions about cosmic size into questions about the fundamental nature of existence. The future evolution of cosmic scale will be shaped by dark energy's continued influence across time periods that dwarf the universe's current age. Current models predict that cosmic expansion will accelerate indefinitely, eventually carrying distant galaxies beyond our observational horizon. In roughly 100 billion years, only our local group of galaxies will remain visible. This temporal perspective reveals that our current view represents a unique epoch in cosmic history. We exist during a golden age of cosmic observation, when large-scale structure remains visible and mappable. Future civilizations, if they arise, will inhabit a much lonelier cosmos, where evidence for cosmic evolution may be difficult to discover. Yet even as the observable universe appears to shrink, the actual universe continues growing larger and more complex. Dark energy ensures that cosmic expansion will accelerate indefinitely, creating ever more space while carrying matter and energy into increasingly dilute configurations. The universe's far future stretches across timescales that make its current age appear insignificant. Stars will exhaust their fuel over trillions of years. Stellar remnants will slowly decay through various quantum processes. Eventually, even the largest black holes will evaporate through Hawking radiation, leaving only elementary particles dispersed through ever-expanding space. These timescales represent natural consequences of physical laws operating across cosmic time. The universe follows its own trajectory, regardless of human preferences or concerns. Yet recognizing our position within this vast temporal context provides perspective on the remarkable circumstances that make cosmic observation possible. Future developments in gravitational wave astronomy may provide new windows on cosmic scale that remain unaffected by electromagnetic limitations. These ripples in space-time itself travel at light speed, but carry information about cosmic events invisible to traditional telescopes. Planned space-based interferometers will detect gravitational waves with wavelengths comparable to planetary orbits, revealing supermassive black hole mergers from cosmic dawn. These observations might probe structure formation during epochs when the universe was opaque to light, providing direct access to previously unobservable periods of cosmic evolution. Gravitational waves from cosmic inflation might carry information about the universe's earliest moments, when quantum fluctuations were first stretched to cosmic scales. Such observations would provide direct tests of inflationary theory and potentially reveal whether our cosmos represents one bubble in a larger multiverse structure. As detection sensitivity improves, gravitational wave astronomy might eventually probe the quantum nature of space-time itself. At sufficiently small scales, space and time might have discrete rather than continuous properties, creating subtle effects that accumulate over cosmic distances and times. It's normal if contemplating these scales and possibilities produces a mixture of wonder and vertigo. The universe operates according to principles that consistently exceed human intuition and challenge basic assumptions about the nature of existence itself. In learning to think about cosmic scale, we discover not just the size of the universe, but the remarkable capacity of human consciousness to transcend evolutionary limitations. We represent something extraordinary, matter organized into patterns capable of contemplating cosmic architecture that extends far beyond any direct experience. The cosmos may be vast and indifferent to human concerns, but it has nonetheless produced, within isolated pockets of space and time, the awareness necessary to comprehend its own structure. This represents, perhaps, the most profound aspect of cosmic scale, not just its enormous extent, but its ability to generate the consciousness required to map its own vastness. These moments of cosmic perspective carry quiet power that transcends intellectual understanding. They connect us to something larger than individual existence, while reminding us of our position as conscious observers, embedded within the very architecture we're attempting to comprehend. The universe maintains its mysteries, even as it reveals its wonders. The scale physics can't show you represents not just a limitation of current knowledge, but an invitation to continue exploring the boundaries of what can be known about the cosmos that surrounds us. In confronting these scales, we encounter both the vastness of space and time and the profound depths of our own capacity for understanding. Each measurement pushes against the limits of what consciousness can grasp, yet somehow we continue finding ways to extend those limits and glimpse ever more distant territories of cosmic reality. The recognition that observable reality may represent only a tiny fraction of what exists should inspire humility rather than despair. We're explorers mapping territories whose full extent may forever exceed our reach, yet the fragments we can observe reveal architecture of breathtaking complexity and beauty that speaks to principles operating far beyond human comprehension. Human beings evolved to understand distances measured in footsteps and territories bounded by horizons, yet through careful observation and mathematical reasoning, we've learned to contemplate scales that stretch toward infinity. This represents perhaps our species' most remarkable intellectual achievement, the ability to comprehend, however imperfectly, our place within the vast cosmic context that surrounds us. The universe unfolds its secrets gradually, requiring patience and persistence to decode. Each generation of observers adds to understanding while discovering new horizons that stretch beyond current reach. This ongoing process of cosmic discovery represents one of consciousness's most profound capabilities, the power to transcend immediate experience and glimpse the architectural principles governing reality itself. As we've seen, the universe operates on scales that consistently challenge human intuition and reveal the limitations of everyday thinking about space, time, and existence. Yet in learning to contemplate these scales, we participate in something remarkable, the universe's ongoing process of coming to know itself through the conscious observers it has produced within its own structure. If this idea stayed with you, you may want to explore next. What happens when space itself breaks down? The physics of quantum space-time. The question of whether consciousness itself operates on cosmic scales leads us into territories where physics and philosophy intersect in ways that remain largely unexplored. Not consciousness as some mystical force that shapes reality, but consciousness as a physical process that emerges from matter organized in specific patterns. If the universe contains infinite copies of every possible arrangement, then consciousness too would be repeated endlessly across space, creating infinite versions of every possible mind. Consider what this means for the nature of awareness itself. The thoughts you're having right now, the specific pattern of neural activity generating your current experience, would exist in countless identical copies throughout an infinite cosmos. Each copy would be having precisely the same thoughts, processing exactly the same sensory information, existing in identical circumstances down to the quantum level. These duplicate minds would be you in the most literal sense possible, not similar beings who happen to think like you, but exact replicas with identical histories, identical neural structures, identical memories. They would remember the same childhood experiences, have formed the same opinions, made the same decisions that led them to this moment of listening to these words. Yet despite this perfect identity, Each copy would exist in complete isolation from the others. They could never communicate, never confirm each other's existence, never share their experiences. The infinite would contain unlimited consciousness while ensuring that each instance remains forever alone with its own private universe of experience. As you contemplate this possibility, notice how it challenges fundamental assumptions about the uniqueness of individual awareness. We think of consciousness as singular, special, irreplaceable. But if space extends infinitely, consciousness becomes as common as hydrogen atoms, repeated endlessly throughout the cosmos in patterns too vast for any mind to comprehend. The physics of information processing in biological systems reveals how consciousness might scale across cosmic distances in ways we're only beginning to understand. Neural networks operate according to principles that remain consistent regardless of their physical substrate. The same mathematical relationships that govern synaptic connections in human brains appear in computer simulations, in quantum mechanical systems, and potentially in cosmic structures themselves. Recent research has uncovered unexpected similarities between neural network topology and the cosmic web's architecture. Galaxy filaments branch and interconnect in patterns that resemble the neural pathways in mammalian brains. These similarities might be purely coincidental, or they might reflect deeper organizational principles that operate across all scales where complex information processing occurs. The cosmic web spans billions of light years, containing roughly the same number of interconnected nodes as a human brain contains neurons. Each galaxy cluster functions like a processing node, connected to other clusters through dark matter filaments that channel matter and energy across vast distances. Information propagates through this network at the speed of light, creating delays measured in millions or billions of years. If consciousness can emerge from sufficiently complex information processing networks, then the cosmic web might support forms of awareness that operate on timescales incomprehensible to human minds. Thoughts that take millions of years to complete, memories that span cosmic epochs, experiences that unfold across distances larger than entire galaxy clusters. You don't need to accept this speculation to appreciate what it reveals about the relationship between consciousness and cosmic scale. The universe operates according to physical principles that naturally create complex, interconnected systems across every scale from quantum to cosmic. Consciousness might not be unique to biological organisms, but rather a general property that emerges whenever matter organizes itself into sufficiently sophisticated information processing networks. The measurement of cosmic time itself presents challenges that reveal fundamental limits on what any conscious observer can know about universal scale. Time flows differently depending on your location in space-time, influenced by gravity and motion in ways that make universal simultaneity impossible. There is no cosmic clock that ticks at the same rate everywhere, no universal present moment that connects all regions of space. This relativity of time creates profound complications for understanding cosmic scale. When we speak of the universe being 13.8 billion years old, we're using a specific reference frame tied to the expansion of space itself. From other perspectives, moving at different velocities or located in different gravitational fields, the universe would appear to have different ages and different scales. An observer traveling at speeds close to light would experience cosmic time passing much more slowly than we do. From their perspective, the universe would age only slightly during journeys that span millions of years from our reference frame. They could potentially witness cosmic evolution across timescales that would encompass thousands of human generations, watching galaxies form and merge in what feels like compressed time. Conversely, an observer located deep within a massive gravitational field would experience time passing more slowly relative to us. From their perspective, the rest of the universe would appear to evolve at accelerated rates. They might watch billions of years of cosmic evolution unfold in what feels like centuries or millennia of local time. These perspectives on cosmic time reveal something profound about the nature of scale itself. The universe doesn't just exist across vast distances. It exists across vast differences in temporal experience, where the same cosmic events unfold at different rates for different observers, where the very meaning of simultaneity dissolves across the scales we've been exploring. The recognition that time itself becomes relative at cosmic scales adds another layer to our understanding of how small we are within this architecture. Not just small in space, but small in our temporal experience. Witnessing the universe from one particular vantage point in space-time, seeing cosmic evolution at one particular rate, determined by our location and motion through the gravitational landscape of reality. As you've listened tonight, you've traveled through scales that stretch from the quantum realm to cosmic horizons that may extend infinitely in all directions. We've seen how the observable universe represents only the beginning of cosmic scale, how dark matter and dark energy comprise most of reality while remaining completely invisible, how space itself expands and creates the boundaries around what we can know. We've encountered cosmic voids so empty that galaxies become invisible across their spans, structures so large they challenge our understanding of how gravity could coordinate their formation, and timescales so vast they dwarf human experience in ways that render familiar concepts of duration meaningless. The mathematics suggest that beyond our cosmic horizon lies more space, possibly infinite space, containing every possible arrangement of matter and energy repeated endlessly throughout an expanse that makes our observable universe appear as a tiny bubble floating in an infinite ocean of possibility. Yet for all these overwhelming scales, for all the humbling recognition of our cosmic insignificance, we remain remarkable. Conscious observers embedded within this vast architecture, capable of measuring distances we could never travel, comprehending scales that exceed our evolutionary capacity for intuition, mapping territories whose full extent may forever remain beyond our reach. The universe has produced, within isolated pockets of space and time, the awareness necessary to contemplate its own vastness. Through careful observation and mathematical reasoning, we've learned to transcend the limitations of human scale and glimpse, however imperfectly, the cosmic context within which we find ourselves embedded. The scale physics can't show you isn't just about larger numbers or more distant objects. It's about recognizing that reality operates on levels that transcend direct human experience entirely, where our most sophisticated instruments reveal only fragments of a puzzle whose complete picture may forever exceed our grasp. The universe maintains its secrets even as it reveals its wonders, operating according to principles that consistently challenge our most basic assumptions about the nature of existence. In contemplating cosmic scale, we encounter not just the vastness of space and time, but the remarkable depths of consciousness itself, the extraordinary capacity for matter to organize into patterns capable of understanding the very cosmos from which it emerged. If this idea stayed with you, you may want to explore next. What happens when nothing exists? The physics of perfect emptiness